are very happy to have Dr. Martin WIESER to give this talk on the production of neutral hydrogen atoms from scattering and reflection of solar-wind protons. Even though Martin could not give this talk in person, so what we are going to do is to replay, the video. But then as you will see, his lecture is very detailed and systematic. And I'm sure that if you have questions, you could ask him or you could write to him. Yes, so we are going to play the video for you now.
Welcome to this talk about energetic neutral atoms generated by solar wind interaction with the lunar surface. My name is Martin WIESER and I'm from the Swedish Institute of Space Physics in Kiruna, Sweden. This image here illustrates the view of the solar wind interaction with the moon that was prevalent in the 20th century. The moon was considered a perfect absorber of solar wind, and downstreams of the moon a vacuum wave could form. This was sort of the origin of this statement, well, the moon is boring, there is not really much going on. However, with the advent of the new missions to the moon, this picture changed dramatically. This is a kind of a collection of all effects which we now know which happen when the solar wind is interacting with the moon. A surprising number of these involve energetic neutral atoms. Most prominent is that about 20% of the solar wind is reflected as energetic neutral atoms to space, but there are also surface materials sputtered which appear as energetic neutral atoms, and there is shielding of solar wind by magnetic anomalies, which again can be observed by looking at the energetic neutral atom emission from the lunar surface. So the image got much more complicated in the 21st century. How are ENAs produced around the moon? There are different processes which can result in energetic neutral atoms being emitted. There is meteorite impact, photodissorption, there is magnetospheric and solar wind ions which precipitate on the lunar surface, which are then reflected back to space, and also they sputter lunar surface material. If you look at the large amount of ENAs that are emitted from the lunar surface, it's this process, solar wind reflected from the surface, and also particles sputtered by solar wind, that is by far dominant. Now, in the first part of this presentation, I will talk about instrumentation, and there, of course, it's important to understand first, what are we looking for? So there are different energy ranges that instrumentation for energetic neutral atoms traditionally cover: low energy ENA, medium energy, and high energy ENAs. For energetic neutral atoms emitted from the lunar surface, it's the low energy ENAs which are of interest, between 10 and maybe 1 or 2 keV of energy. Species-wise, this is fast neutral hydrogen, helium, originate from the solar wind, but also oxygen and other heavy elements from the lunar surface. Instrumentation should be able to resolve direction for these particles and should have time resolution of the order of seconds to minutes. Flux-wise, we are talking about emissions which are maybe 1/1000th of the solar wind flux. There are not so many instruments which have been observing the moon in energetic neutral atoms which were built for that purpose. This is an overview of dedicated instruments observing the moon. So we have IBEX low, which as a byproduct of its primary mission to observe the heliosphere, also did look at the moon. We have the Senna instrument on the Indian Chandrayaan mission, which has been orbiting the moon for almost a year. And we have the ASSAD instrument on the Chang'e 4 mission, which is on the surface and mounted on a rover. I will describe a typical ENA instrument at the example of the Senna instrument on Chandrayaan. The Senna instrument on Chandrayaan is part of an instrument package called the Sub-KeV Atom Reflecting Analyzer, or Sara. Sara consisted of 3 units, an ENA imager, a solar wind monitor, and a common DPU. Sara was a precursor of what is now flying on Bepi Colombo, on MMO and Ampio to Mercury. So at the time, the Sara instrument was considered to be a test case to see how solar wind is interacting with surfaces. And as it turned out, a lot of new effects were observed by this instrument, which of course now will also happen when the Bepi Colombo instrumentation arrives at Mercury. This is how the instrument looks like. So it's a 2 kilo instrument, and the size is of the order of 20 centimeters wide along the longest direction here shown. The half circular part is the entrance system, which I'm going to describe a bit in more details in the following slides. It's not so easy to measure energetic neutral atoms at energies below 1 keV. The problem is, well, they are neutral, so they cannot be directly influenced with ion optical elements. They behave similar as photons, but their flux is much lower than a typical UV photon flux encountered in the corresponding environment. And for direct detection, for example, with microchannel plates, the detection efficiencies are really, really low if you go at energies below a few hundred eV. The way out of this is to convert the energetic neutral atoms to ions by reflecting them at grazing incidence from suitable surfaces, and subsequently analyze them using conventional ion optical elements. This graph shows the overall detection principle applied in the Senna instrument on Chandrayaan, but it's actually very, very similar to the 2 other instruments which have been used to observe ENA from the moon. That's IBEX, the IBEX low instrument on the IBEX satellite, and as well as the ASSAD instrument on the Chang'e 4 mission. So in general, one has to first reject particles which are unwanted in the detection process. And this is group 1 here on the top left, where first ions have to be rejected to as high energy as is affordable. In the case of the CNA instrument, ions up to about 10 keV are rejected in this ion rejection section. Then the remaining energetic neutral atoms are ionized on a suitably chosen conversion surface by reflecting them at grazing incidence. The ionization yield will depend on energy. It will also depend on species, which is one of the aspects which makes data analysis from the Sara instrument quite an involved story. After particles have been ionized, they are analyzed using conventional ion optics. In the case of CNA, there is a wave-shaped energy analyzer, which provides an energy resolution of about 1. That means it's a rather coarse energy resolution. But again, this is what is needed for this type of instrument, because the energy analysis is sweeping through the energy range, And if the energy resolution is too high, then too many steps are needed, and the duty cycle will lower the sensitivity of the whole instrument. After passing energy analysis, time of flight section is used for velocity, and of course then combined with no energy for mass analysis. I've been mentioning interaction with surfaces. So a particle is ionized when interacting with the conversion surface at the entrance of the instrument. But particle surface interaction is a rather complicated story. So for an incident particle, an ion or a neutral atom onto a surface, various processes may happen which result in different products emitted from the surface upon this interaction. Mainly, there is secondary electrons produced by incident ion or neutrals. There is the incident particle, which may be backscattered away from the surface again, or it may produce recoils, which are single collision particles. So the red original particle gets buried in the surface, and one of the top atoms of the surface is knocked out. But there is also sputter particles which originate from the bulk of the material of the surface. And all these emitted particles, they experience change in energy relative to the incident particle, as well as change in direction. So the key here is to find a material, a surface material, that forces a certain parameter of this interaction into a desired range. In the Senna instrument, there are two types of surfaces. So there is the conversion surface, which is optimized for a large positive ion yield, shown on the top left. The surface is a magnesium oxide layer on a highly polished silicon wafer, which guarantees that the angular scattering properties are not increasing dramatically upon interacting with the surface. Normal technical surfaces are very bad in retaining the direction, the specular direction of a reflected particle, as the surface is really rough. So a large, big work was invested in getting these surfaces here as flat as possible. Then we have a second application of surface interaction inside the Senna instrument. That's in the time of flight section. There we chose a single crystal tungsten surface, which is optimized for a large electron yield, and due to the high mass of the tungsten atoms compared to a typical projectile, which would be, for example, hydrogen or oxygen, there is not much angular scattering involved, and also the energy loss is affordable. But again, these surfaces, they are highly polished and are kept at conditions which guarantee that there are no contaminants on it. Because, for example, water on the surface, it will produce recoils. One would imagine an oxygen atom is hitting the surface at grazing incidents, and there is always a chance that instead of the oxygen atom be reflected back as scattered particle, one will get a hydrogen particle, which was, for example, absorbed on the surface. If you now look a bit more at the overall ion optics of the Sara instrument, then it looks like this. So we have a half-circle shaped entrance system where on the outermost radii the ion deflector is placed. It's also shown here. And then also half-circle shaped conversion surface, which converts incident neutral atoms to ions. The signs are then accelerated towards this central point here in the middle of the optics, and it corresponds in the 3D view here to this section here. And while they're accelerated inwards, they're also energy analyzed in the wave-shaped energy analyzer. Afterwards, they travel away from the symmetry axis again, hit a time-of-flight start surface, where an electron is emitted, which is collected. It's shown here. The electron is accelerated upwards to a start detector, and the particle, which was an ion when it was red, but mostly now will be converted back to a neutral atom, travels on in a straight line to a stop detector, which is then used to determine the direction the particle actually entered the instrument in the first place. As we have two surface interactions involved, the angular resolution has fundamental limits. So there is scattering away from the travel direction here at the conversion surface, but we also have scattering away from this ideal direction, which is shown here at the start surface, and the remaining angular resolution, which is possible from this arrangement, is of the order of about 45 degrees. Ultraviolet light is also a major problem for this type of instruments. That, of course, because photons are not charged, they will follow the same trajectories as the energetic neutral atoms. And similar to energetic neutral atoms, photons hitting a surface with sufficient energy, they will emit photoelectrons, and those are hard to distinguish from secondary electrons generated by energetic neutral atoms. For this reason, all surfaces inside of the instrument are blackened. In this case, copper sulfide coating was used, combined with this sawteeth-like grooves, and which result per reflection about in a suppression of 10 to minus 3, and with 3 reflections needed to get into the time of flight section, we have about 10 to minus 9 suppression of incident photons. In this picture, the photons, they would show up from the right-hand side and mostly be trapped here in this kind of V-shaped groove, and those which hit here on the top, of course, have a probability to be forward scattered, but only with very low probability due to this very foamy black surface structure. After particles have been detected by the start detector, which will give an indication from what direction a particle originated from, and of course also by the stop detector, giving a coincidence detection. Quite a large amount of processing is needed to convert these events into something which is later downlinked. So this chart here shows an overview of how individual TOF events are processed with the internal lookup tables, which compensate, for example, for different path lengths in the time of flight cell, mainly due to the fact that the stopped microchannel plates are 4 flat pieces, so one gets a bit different path lengths depending on whether one starts, for example, on this start surface and hits this MCP, or one starts on this start surface and one hits this stop MCP here. Also, there is compensation for energy because the data product contains mass bins which are not energy dependent. And additionally, of course, non-correlated counters are taken along in the whole processing step, and the result is an energy mass matrix, which in this instrument was called accumulation matrix, and there is a matrix with uncorrelated counters, which was called accumulation scaling matrix. The values of these tables, they were determined during calibration, and they were updated accordingly. some data from calibration runs. So the instrument is measuring mass using time of flight data. So here we have the mass response, or the time of flight response to different species incident on the instrument during calibration. We will note that it's ions which are incident. That's because it's much easier for a calibration purpose to generate ions. In order to record this mass spectra, the ion deflection system at the entrance of the instrument was turned off. And the obtained mass resolution is, well, it's about 2 to 3. So it's not a very high mass resolving instrument. But the main thing here is that hydrogen is very well separated from masses which are close to oxygen. So we have carbon here, mass 12, water with mass 8, and the oxygen peak would sit about here where I currently place the cursor. Hydrogen and oxygen are the most dominant species which were expected. Hydrogen because solar wind, and oxygen because it's the one of the most abundant elements in the lunar regolith or rock in general. Now we were using ions to show the performance, but of course there also has to be proof that the neutrals which interact with the charge conversion surface at the entrance of the instrument produce the same response. And here is some data obtained from the flight model calibration. So there is, so as solid line, the ion data shown, and as dashed line, the data from the actual spectrum obtained from incident neutral hydrogen, and they match pretty well. So we are confident that the ion calibrations done before are representative for the response to energetic neutral atoms. If this is all combined, this is what we get. So a brief overview of the Chandrayaan-1 energetic neutrals analyzer. So we cover an energy range of about 10 eV to about 3 keV. There is a rather sizable geometric factor needed to get a reasonable amount of counts. But then the total efficiency for the detectors is only 1%. And the reason for that is that energetic neutral atoms are not so likely to convert to positive ions after interacting with conversion surfaces. So there is the largest loss in efficiency. Then we have an angular resolution, which is here shown as 9 to 25 degrees, but that's of course the angular resolution of the time of flight system. But as there is azimuthal scattering involved at the two surface interactions, the effective resolution is, as mentioned before, about 9 times 45 degrees. Some data processing can be done to deconvolve this, but for imaging mapping, like I will present in the second part of this presentation, a realistic value which was obtained in lunar orbit was 45 degree azimuthal resolution. That was part 1 of my presentation. In part 2, I will talk about the science and science result obtained by this instrument. And also, I will talk about another instrument which we currently have on the lunar surface, about the ASSAD instrument, and present science data obtained by it. In part 2 of my presentation, I will show science results obtained from mainly Chandrayaan-1 and also a bit from the ASSAD instrument on Chang'e-4. First, view back on the slide, which I've been showing already. So these are the observers for energetic neutral atoms emitted from the moon. We have IBEX low, far away, Chandrayaan-1 in the orbit around the moon, and we have the ASSAD instrument on the lunar surface. I will first focus mainly on Chandrayaan-1 data from orbit. As shown previously in the instrument section, the Senna instrument, it has a fan-shaped field of view, and it's used in this type of push broom geometry, where the center pixel looks in nadir direction down to the surface, and using the orbital motion of the spacecraft, we scan over the surface and over the turn of the whole mission, orbit after orbit, we get the complete picture of ENA emissions from the lunar surface. This is some of the first data we obtained from Senna, and it was clear immediately that there is a rather large fraction of energetic neutral atoms which is reflected back from the surface. The lengths of the needles shown here correspond to flux, and close to the equator the flux is largest, and towards the poles it gets less and less. And this is of course an effect of the cosine of the solar zenith angle. If you look at the energy spectrum, one can see that the neutral atoms emitted from the surface, they follow the solar wind energy spectrum. So here we have two spectra shown. There is the spectrum of the energetic neutral atoms, the three lines here on the left, and we have a solar wind spectrum, which is a bit broader than in solar wind, in undisturbed solar wind, because we are behind the pole shock, so it's a bit heated. But nevertheless, one can see that the intensity of the reflected neutral atoms, it follows the intensity of the solar wind. So this dotted line, for example, which has the lowest ENA flux, it corresponds to the lowest proton flux onto the surface. And also the cutoff energy for the energetic neutral atoms, it sort of shifts to the left when the solar wind energy is getting smaller. Also notable is that there is typically energy loss of about 50% from solar wind protons to the energetic neutral atoms emitted from the surface. These energetic neutral atoms were also observed further away by the IBEX mission. Here is energy. Here is an angular spectrum shown as observed by IBEX low. So we have the IBEX instrument, which is on a spinning spacecraft, and every time the instrument's field of view sweeps across the moon, there is this faint line indicating that the moon is a source for energetic neutral atoms. If you now move closer again to the moon, then Chandrayaan also carried a solar wind monitor. And part of the field of view of this solar wind monitor was actually looking down towards the surface. And this is what was obtained when mapping the proton flux measured by this instrument. We see in color the ion flux, and the black contours is the surface magnetic field. And obvious correlation is there. So where there is a large surface magnetic field, there is a large proton flux originating from the surface. And we observed about up to 50% of the solar wind flux is reflected back to space like that. Then, of course, one starts to think, and if protons are reflected back to space, it means that less protons precipitate onto the surface. And as protons are reflected from the surface back to space as energetic neutrals, one would expect that the energetic neutral atom flux is depleted when a magnetic anomaly deflects the solar wind proton flux away. And this is exactly what was observed. So here we have orbital paths across the Gerasimovich magnetic anomaly on the far side. And we see on the top panel that the energetic neutral atom flux indeed is depleted just when passing over the largest local magnetization in this anomaly. The anomaly is interesting if you look at this Zone 8 image. So the anomaly is sitting here in the center, and it features this swirl type of surface albedo features, which are also also visible on the lunar near side, for example, in the Rainer gamma region, which is also a magnetic anomaly. The swirls are sometimes a bit hard to see. So if you go to the right here, it's a Clementine image. Here they're almost invisible. And if I put some markings on top of this, so we have the red circle, which is about the extent of the magnetic anomaly, and now also in this Clementine image, this surface feature become visible. The surface feature are thought to originate from interaction between precipitating solar wind, local magnetization, and possibly how regolith grains move around in this environment. If you now go back to energetic neutral atoms again, so this is the same view. On the left, you have the Gerasimovich magnetic anomaly in the center, and in color shown is the energetic neutral atom flux. And it's clear, while above the most intense magnetization, there is a depletion in the flux visible, and around the magnetic anomaly there is an enhancement. At the same time, just above the magnetic anomaly, intense proton reflection is observed. And of course, well, the protons which do not reach the surface inside the anomaly, they have to go somewhere, and some of them are reflected back to the spacecraft, which passes in about 100 or 200 kilometer altitude above it. Then it's of course the question, is this now a feature of the magnetic field, or is it a feature maybe of the surface itself that has different reflection properties? And by comparing two measurements with different solar wind dynamic pressure, we conclude that the magnetic field is really the driving force behind this depletion in ENA flux observed from the surface. So these two measurements, we basically double the dynamic pressure of the solar wind protons, and one can see that this depletion, which is visible for the lower dynamic pressure, it's almost flattened down to the ground, and only very small areas still show this reduction, and that's of course the areas where the magnetic field is strongest. How much of the solar wind flux is shielded from the surface by this anomaly? Vorburger et al. Did a rather extensive study with all the Chandrian data, and here we have the summary, the statistical summary. So we have on the x-axis the magnetic field strength as observed by Lunar Prospector in 30 kilometers altitude, and on the vertical axis the shielding efficiency for the solar wind. And it corresponds nicely to increased solar wind dynamic pressure, results in less shielding, and also a stronger field increases the shielding. But still, the shielding of the solar wind is typically less than 50% in all the observed cases. If you look a bit more at energy spectra observed when passing over such a shielded region, then it's notable that the energy spectrum gets softer when directly above a magnetic anomaly, as shown on this plot here on the left. So the red spectrum is while inside the magnetic anomaly, and the blue and the green spectra are from the regions around. And this is interpreted as the buildup of a surface potential of about 150 volts, which slows down the solar wind protons before they interact with the surface. And of course, as they lose their charge when interacting with the surface, their energy loss, which they experienced while they were still protons, is retained in the ENAs which we observe from orbit. And this is then interpreted as the formation of a mini magnetosphere above magnetized regions on the moon. A bit more statistical view. So we move away now from the Gerasimovich anomaly to a more global view of the moon. And here also I can show that generally the magnetic field strength, it corresponds to strong proton reflection, which is the middle plot, and it corresponds to depletion of backscattered ENAs. The Gerasimovich anomaly we were looking at now the previous slide. It's placed here, it's this dot, so it's this enhancement and it's this depletion here. But there is a much larger magnetic anomaly in around the South Pole Aitken basin, which has a much stronger effect on the ENA depletion, which is clearly visible here as this blue area. If you now move a bit closer to the surface, there is the question of how is the solar wind, which is neutralized and backscattered as neutrals, how is that angularly wise emitted back from the surface? What is the scattering function? And there it of course matters what the solar wind or the protons which hits the surface, how well they are collimated. And so we can distinguish three cases of angular emission functions from the surface. We have a rather well-defined angular shape when undisturbed solar wind is hitting the surface. So there is a solar wind is this black line from the left entering. We have a forward and a backward scattered fraction. As soon as we go into the magnetosheath, the temperature of the solar wind increases and it's directionally less well defined, and this angular scatter function gets more and more uniform. And inside the plasma sheaths, where there are mainly magnetospheric ions, the scattering function has no longer an angular preference. This data is obtained statistically from orbit, and of course there remains the question, is this really the picture as it looks like on the surface, or is kind of intermediate layers between the surface and the 100 or 200 kilometers altitude the spacecraft observes, are the particles changed in this intermediate layer? And to address this question relatively quickly, after the Chandrayaan mission showed that ENAs are emitted from the surface, there was this early concept drawing of how one could investigate ENA emission directly at the surface. So the idea was to have a lander and ENA imaging instrument mounted on a rotating platform, which would allow to investigate different emission angles from the surface while the solar wind precipitates from above. This also would allow to assess the question in orbit measurements. They are averages over several square kilometers, and maybe there is a variation on the meter scale. Now, this concept here, it didn't happen, but what did happen was the ASSAD instrument on Chang'e 4. And this is how it looked like. So the Chang'e 4 mission, it has a rover called U22. And on this rover, the ASSAD instrument is mounted here on the front side, and it's looking at the spot on the surface in front of the rover. And as the rover is moving around, different surface areas can be inspected. And also the rover has different orientations relative to the impinging solar wind. So the angular distribution can be investigated. The ASSAD instrument, it's a single pixel instrument, so it requires the rover to move around to obtain the science data. But internally, it's actually built almost identical to the Chandrayaan Senna instrument. So it has exactly the same functional groups. It features charged particle deflection system, a conversion surface, energy analysis, and the time of flight system. Here on the right, a bit more precise is the observation geometry shown. So we have the rover and the projected field of view on the surface, the surface patch from which emitted energetic neutral atoms are collected from. It's about 2 meters long and maybe half a meter wide. And as I said before, the motion of the rover is used to inspect different surface patches. Chang'e 4 landed on the 3rd of January on the far side of the moon, which was in itself a first, as it's the first lander on the far side of the moon. In the Von Karman crater, which is in the South Pole Aitken Basin, which contains the magnetic anomaly I've been describing just before. ASSAD observations provide the first ever ENA measurements on the lunar surface. And since landing, the instrument is operating typically twice per lunar day. That's due to thermal constraints from the rover. And it collects per lunar day, on average, maybe 3 or 4 hours of data. If we look at the statistics of the obtained data, it's quite well distributed over different solar azimuth angles, different solar wind and EMF interplanetary magnetic field conditions. The instrument is still going strong, so we have just recently reached the 2-year mark of operations on the moon, and there are still no signs of degradation visible. What does the instrument see? So ASSAD has mass resolution capability, and shown in this plot is mass separated spectra, ENA spectra as obtained from the lunar surface. And you see the top panel, there is a rather intense energetic neutral hydrogen emission, which is solar wind driven, especially the high energy cutoff energy of about 1 keV is the average solar wind energy. But then we are also able to separate out heavier elements, oxygen, which is dominant at much lower energies, and even heavier elements like elements like silicon, which also make up a large fraction of the rock. And those are clearly visible above the noise level, which is shown here by a dotted line. Current work is going on about modeling this spectra, these shapes of the spectra here, to understand how different parts of the observed spectra came to be. For example, here is rather strong tail towards higher energies for oxygen, which is not visible in the silicon group, for example. But this is work in progress, and the data accumulation from the ASSAD instrument is still ongoing. So to conclude, I would like to come back to this nice drawing made by my colleague Futana-san, which illustrates all the different interaction processes which have been discovered on the moon, which happen when solar wind hits the surface. And indeed, the moon is not a boring place. The moon is very exciting, and it also turned out to be, it's a very complex place. And with this, I would like to close. Thank you very much for your attention.
Actually, this talk is very, very clear and detailed. I mean, it's very, very systematic. Unfortunately, Dr. Martin WIESER could not give the talk himself, that we could not arrange the talk on time. I hope that we will have some other time that, he could give the talk in person. This talk concluded to some extent our first part of the solar wind interaction of the moon, and also together with Dr. Andrew Pope's talk. So we have a rather complete set of presentation on the solar wind interaction. So thank you.